Joseph Miller, who is coming from Stanford. His background is that he was a graduate student at Texas in Austin, a graduate student of Natasha Pavlovich, which means he is my mathematical grandson. So please welcome Joseph, who will talk to us about effective dynamics of interacting classical, quantum, and wave systems.
Thank you so much for inviting me. So I heard it's mostly a PDEs room. So I'll be talking about how to get PDEs from many particle systems. It's the overall goal. Okay, so first I'll give it a little introduction on like the mindset that I want to have for what kind of problems I care about. Then we'll talk about the Vlasov equation. So all of these will be kinetic equations. In particular, how you can actually derive the Hamiltonian structure of this equation from the many particle level. Then we'll go on to including collisions. So I'll give two examples of collisional kinetic theories. One is the Boltzmann equation. The other is an equation on like wave turbulence. So it's called the four-wave kinetic equation. So I'll talk about the hierarchies and the problems there. The next, I'll talk about how do I think about mixtures? How do I derive PDEs for a mixture of gases? And then last, if I'll have a bit of time, I'll talk about the quantum picture. And there we use a little bit different tools, those coming from second quantization. Okay. And again, if you have any questions or want me to explain things in more detail, this is at the level of kind of more physics, because there's a lot of things I want to talk about. So just stop me if you want details. Okay, so just a little bit of a prelude. Kinetic equations are a class of differential equations, usually integral to differential equations, used to effectively describe large interacting systems of particles. So the first example for non-collisional, I just have n ODEs for different particles running around in space, is the Vlasov equation. So you can, depending on the sign of the interaction potential, it can either model plasmas, so fully ionized gases, or galaxies for the attractive case. For dilute collisional gases, so microscopically what they look at like is I have a bunch of hard spheres bouncing around in space. You can derive the Boltzmann equation. On the quantum side, there are actually two types of equations you get. So there are two species of statistics. One is for bosons, where I basically just get symmetry across my wave function. And in this case, you actually get the Hartree equation as your limiting theory. If I have fermions, I get a minus sign popping out when I interchange particle labels. So in this case, I get the Hartree-Fock equation, which is slightly more complicated. Next would be wave turbulence. So instead of viewing things as many particles, I can view many waves. Look at the interactions between many waves. And from this, you get the kinetic wave equation. And a few extra examples would be for collisional plasmas, you have the Landau equation. So one way to see this is there's actually no way to derive it that I know of without going more probabilistic or in 2D or using very hard methods. But you can view it as a grazing limit of the Boltzmann equation. And for example, things like crowd dynamics, you get equations like the Hamilton-Jacobi equations. Yeah.
What's a quantum gas?
So a quantum gas, I just mean a gas comprised of quantum particles. So I have n quantum particles. Let's say I have, for each of these, I have, let's say like 10 to the 20 equations. Let's say I'm trying to model a gas in a box, right? Each of these equations, like I wrote down here, is actually like the Schrödinger equation is a linear equation. So microscopically, I understand the dynamics very well, but numerically, I can't simulate that at all, right? If I had 10 to the 20 equations. So on the left-hand side of these, the physical theories, there's only a finite number of particles we ever care about in reality. But the way we describe them effectively is via one nonlinear PDE, right? So going from the left to the right is what I call a derivation problem. So if I take, how do I statistically take a very, very high dimensional system of coupled equations and then compress all of that information into one nonlinear equation? There's also another way, it goes the other way too. If I care about numerics, for example, let's say I'm caring about simulating plasmas. So what you can do is you can start with something like the Landau equation, and I can make a particle method, right? So I can go the other way, put it back into the particle world. However, when I do this, often what you're looking for in order to be computationally useful is something that's not really a physical particle method. So if any of you know Boltzmann, like Bird's algorithm is one of these. And so I can go the other way too, and that actually informs numerics. Any other questions? Okay, cool. So I'll just be talking about the first few of these. Okay, so let's talk about the Vlasov equation. Here I have the Vlasov equation. The way I think about this is F is going to be a probability distribution on positions in velocity space. And what it'll be mostly is transport. So this is just the free transport. And then there'll be some interaction coming from the gradient of an interaction potential convoluted with rho f, where rho f is just the position density. So I'm integrating out the velocity degrees of freedom. So this is a very classical equation. It was written down by Vlasov and I think slightly earlier by Jeans, but in a different for galactic dynamics. So in d = 3, the physically relevant potential is this Coulomb potential. So with a minus, it models plasmas, and with a plus, it models galaxies. Okay. So there's many different ways to derive this equation, starting from discrete or particle level. The first kind of the most simple way is, let's say I take n ordinary differential equations, where xi denotes the position of the ith particle, and vi is velocity. Okay, and here the t just means time. The way they interact is by, if I take the time derivative of the ith particle's velocity, so its acceleration should be equal to, let's say it's some mean field, so that means 1 over n, and then I sum over the interactions between the particle I, its position, and particle j. And I do this for each I between 1 and n. So in practice, n is huge, right? So how do I condense all of this information into one PDE? What you can do is you can look at this thing called the empirical measure. So at each time t, I form this measure mu n by just averaging the Dirac centered at each of these points, xi and bi, and look at its evolution in time. So you can imagine I have a bunch of points, and I just put a Dirac on each one and then consider that measure. As n goes to infinity, this should be still a reasonable theory for any n. And actually, you can show that if W is nice enough, in particular, the C11 means I can control the flows of this well enough, then the empirical measure will converge to a solution of Vlasov. So what I mean by converge to a solution of Vlasov is if the initial data converges, then for every later time, it will also converge. So either I solve these n PDEs or n ODEs, or I solve the one PDE. That's the way I do this. Okay. Great. Now there's another possible way to derive the Vlasov equation. So instead of taking each of the ODEs, solving it, and then looking at the empirical measure, the Dirac centered on each of the points, I can instead consider each of the variables as random variables. And what I'll get is if these random variables satisfy that ODE, basically by the chain rule, the law of the n particles should satisfy this equation, where Fn is a function on R dn. Right, so the phase space, the n particle phase space. Now, if each of the particles is identical, right, I'm trying to figure out statistics of this gas. If they're identical, F actually has some extra properties. It satisfies this equation, and it's symmetric whenever I permute particle labels. So it doesn't really care where particle, if I flip the positions of particle 1 and 2, those are statistically the same. Okay. The way you can start to get an effective theory, starting from this Liouville equation, is you can define a marginal. So what this object is I take my n particle system, I have n particles in a box, and then I just integrate out the degrees of freedom. I look at only k particle subsystems. So I pick a smaller subsystem. Now, if I do this, each of the Fn k's, so these objects here, and I plug it back into this equation and see what I get. If I assume that my particle labels are invariant, I'm allowed to flip particle labels, you can derive what's called the BBGKY hierarchy. And so it's a big formula, but here, this is just the Liouville equation, right? But for the K particle subsystem. So what it's saying is on the left-hand side, I just look like free transport, is what this means. But there's a correction, which is of order 1 as the capital N, which is the number of particles goes to infinity, which looks like this. So it's coupled to the K plus first subsystem. So I have a K particle subsystem, and this quantity is saying, okay, what's the effect of me adding exactly one new particle in, and then it collides with something in my system. And so it could collide in many different ways. It could collide with any one of the particle labels before me in the K particle system. And it could be, and I have to average over all possible ways it could happen, right? And so this gives me my energy of the next thing. So this is kind of the conceptual way I view this thing. This is a correction coming from, I add one particle to my system. So what we can do now is before, if I take Fn and just tried to take a limit as n goes to infinity, that doesn't make sense. But if I look at each of the marginals and then take n to infinity, I can, I just have an infinite hierarchy of equations. So the term that was 1 over n disappears from before. And I'm just left with transport equals minus, and then this term I was talking about, which comes from the correction. This is a typo. This should be I goes from 1 to k. Okay, so it's a linear system. If I view it as a vector, I take fk. So I'll use this notation. So if I have this, k goes from 1 to infinity. It's linear with respect to this full capital F, but it's coupled. All of these equations are coupled. So if I want to solve, for example, like F1, I need to know F2 and F2 to F3. Okay. However, there's a really special solution that can pop out of this. If I plug in a tensor product, so corresponding to, if you like probability, like the IID, so identically independent, identically distributed, if I view these as random variables, then actually solutions of Vlasov, the Vlasov equation I wrote first, end up being solutions of this PDE if I product them together like this. So this is called the tensor product. And it corresponds to IID data. Okay. So this is another way to see I get the Vlasov equation. If I start with something, it's known by Spohn back in the, I think, 80s, that this hierarchy has unique solutions. So if I start with something that's initially IID, so initially looks like a tensor product, then solve it, and just check that this solves the full Vlasov hierarchy, then I've constructed solutions that are unique. So that those must be the only solutions. Okay. So to me, this hierarchy is a generalization of the Vlasov equation. It's generalized to initial data, which is not chaotic, so I drop independence. So there. Okay, so this is a big slide. So I said before I wanted to talk about the Hamiltonian structure of the Vlasov equation. So the Vlasov equation is a PDE which has unique geometric information hidden in it. So it means that I can write it, the Vlasov equation, as a infinite dimensional ODE, Hamiltonian ODE. So here's the exact definition. If I let G be a Lie algebra, where G is some function space, I'll take smooth functions for our case. We can view elements of G as observables, and then functionals in the dual as states. So my solution to the Vlasov, I want to view as some element of this G star. So the dual, if you take G to be smooth functions, the dual of it is compactly supported distributions. So this makes sense. Okay, and so if I just do this formal construction, and you give me a Lie algebra, it's a very old fact that it creates a geometric structure on the dual. So it's given by this bracket here. This bracket, D, just means the Gaussian derivative. And let's see. This makes sense and is a fully valid definition. It gives a nice structure for finite dimensional things. For the Vlasov equation, if I take an infinite dimensional G, this may no longer make sense. So I'll talk a little bit about why. Anyway, I get the structure. And I define a PDE to have a Hamiltonian structure if there exists a Lie-Poisson manifold, so there exists a geometric structure and a Hamiltonian such that it looks like this, this equation.
There is a topology on.
There's a topology on
the
that.
space,
Yep. So that was part of the, so this is kind of just an algebraic slide at the moment, right? I'm just forgetting all functional analytic issues, but that is something we ended up talking about. Okay. Okay, so let me describe what it is, at least formally for Vlasov. So if I have just the regular Poisson bracket on RD, R2D, it's given by this, right? Where there's a phi and a psi. And this is the regular Poisson bracket. I view this as a Lie bracket. It satisfies all the properties of being a Lie bracket. And if I do this construction by Lie, you get a big manifold, and you get this formal Hamiltonian that is equivalent to what Vlasov ends up being. So the Hamiltonian here is quite intuitive to me. It's the kinetic energy, whatever F is, and then this is the potential energy. So it's plus the potential energy. So rho F again is just the position density of F. So at least formally, you can write your Vlasov equation as being this very nice Hamiltonian vector field, as being the flow of this very nice Hamiltonian vector field, where I'm characterizing its action by the bracket I defined before. Okay, so there is structure for the Vlasov equation, just on the formal level. Okay. Another interesting thing is there are two other equations we've already seen have this nice structure. One is the Liouville equation. This is just the n particle energy, right? So it's the kinetic energy plus potential energy. And also there are the BBGKY equations. So here, this one is much more complicated. You actually have to define a Lie algebra structure. But what it does is it takes solutions of Liouville and maps. If I look at them under this map, taking the marginal, it actually preserves its geometry. So whatever the geometry I put on this space is, it preserves the notion of marginals. Very nice. So there are a few things that were left unanswered though with these two observations. One is all of this is formal so far. How do I actually put topology on this? How do I make sense of it like an analyst? The other is there's no notion of taking a limit as n goes to infinity here. It doesn't seem to make sense. I can't seem to relate the Hamiltonian structure of the Vlasov equation, which kind of just looks like it just exists. We don't know why. And these natural structures. Okay, so this is joint work. We figured out how to do this with Andrea Namhod, my advisor, Natasha Pavlovich, Matt Rosenzweig, and Giulio Staffolani. We basically just, in short, proved this diagram. So if I start from Newton's equations at the beginning, I can put some geometric structure on there, Hamiltonian structure. I can view it two ways. One is I take the probabilistic law and I get Liouville's equation. I can put a Hamiltonian structure there. If I take marginals, I can get BBGKY and get structure there. And then if I take a limit as n goes to infinity, we were able to define a Hamiltonian structure on this huge object, such that when I take the Vlasov equation and look at its tensor products, so if I look at just this guy, so F equals this, then it'll take solutions of Vlasov to solutions of this, and actually this mapping we show is what's called a Poisson morphism. So in short, this is kind of an algebraic paper. Everything here makes sense, commutes, and preserves the geometry. Okay. Okay, so let's move on from this. This is just one way to think about how do I transfer behavior from many particle system to like the PDE, and how do I get information back and forth? This is an example of a way to do it that's more geometric. Okay, the next equation I want to talk about is the Boltzmann equation, which is the first example where I have collisions occurring. Instead of having an ODE with a continuous flow, the Boltzmann equation models what happens when I have hard sphere collisions. So I have two particles. You can imagine them going in, And then they instantaneously, when they meet each other, they instantaneously change velocities and go out. So the limiting effective theory you expect, and what Boltzmann wrote down is this one here, where on the left, I just have transport of my particles. And on the right, I have this Q of FF, which is a bilinear collision operator, where here B of V1 minus V2 sigma is some weight corresponding to how I weight the difference in velocities. And the stars on the V1 and V2 mean post-collisional. So I look at pre-collisional velocities and then post-collisional velocities. And then I look at the transition probability that this occurs and then average over all of those. Okay. The way you can derive this equation, and so this was done by Alexander and Lamford, and then there's a big textbook by Gallagher, San Ramon, and Texier in about 2012, where they started with n identical particles of diameter epsilon and formed what's called the Boltzmann hierarchy. So before I looked at my law of my particles, right? I got some equation that looks like BGKY. So I have some finite approximation, and then I take n to infinity, and I get this infinite set of coupled equations. The way I see that this recovers Boltzmann in the same way that the Vlasov hierarchy recovered Vlasov is I look at tensor products. And in particular, this collision operator, I don't really want to write it down, but it behaves very nicely with respect to tensor products. So it recovers this Q. Now, the way you should think about this sum here is I have a K particle system. So I view this as K particles, and then I inject the one extra particle into it. It's called K plus one. And there's many different ways it could have hit some particle that's in my system. So in particular, there is some index I where I'm hitting particle I that's in my system. So that's what this sub I stands for. Okay. So the way I view this anyway is more in terms of its mild formulation. So again, if I define T superscript T to be the transport operator, I can rewrite my equation using its characteristics as this equation. So f of k, so the k particle system, k particle subsystem at time t, is equal to just whatever the free transport was of my initial distribution. And then there's some correction coming from a bunch of collisions. The way I view each of these collisions is, let's take the very simple scenario where I go from 1 and I just have one new particle incoming. At time 0, I know everything, right? And so I propagate it up to some time s, that's what this mild formulation tells me, and then I inject in a new particle that's colliding with velocity v2 and scattering angle sigma. What this will create is a flow that keeps going backwards until this t, and then I evaluate at f of 2, f2. Okay, and so this is just for with k equals 1 to 2. Okay, so if I want to understand this hierarchy, I have to understand very complicated expressions like this. So I prefer to think about it pictorially. Oh, is the picture clear? Okay, so, okay. Yeah, and so what we can do is we can now iterate. Notice I have an f of k, depends on fk plus 1, but then I just keep putting it back in, keep using the formula iteratively. And so what I'll get is trees that go this way. And I'm trying to understand what happens to all of these trees. Okay, so if I do this, this is an example of one of the things that I see. Right? So I take a two-particle subsystem, and then I start iterating iterating in time. And I have successive collisions. And so I've labeled the collisions occurring at T0, T1, T2, T3, and T4. Now the idea is if I turn this back into formula, it's just a composition of C's and T's, right? If I turn this back into formulas, I just have, there's gonna be a T, there's going to be a C, and then there's going to be another T, et cetera. Keeps going. But the issue is there's going to be a lot of sums. So I sum from I equals 1 to k. And then the next one up will be sum I2 goes from 1 to k plus 1, et cetera. If I just try and do some estimates and try to show well-posedness, these sums end up being very bad for me if I don't use something else, right? I get basically like factorial number of terms popping out. And if I do that and do it really naively, I can't close any argument. Can't close any estimate. So the idea is, well, what you would like to do is somehow look at these pictures. I'm summing a lot of them, and you want to group terms that behave similarly together so that I can close my estimates better. So there are two pictures that I feel like should behave the same. So the first one is if I just collide at this time T2, I collide particle 3 with particle 4. So particle 3 just continues on. Particle 4 has another collision. Okay. And same with this one. So particle 1 collides with what I'm calling particle 5 and continues on. This behaves really similarly to this other one, right? Where I've just switched the times. They're actually exactly the same in this case. So if I just go by this way, and this occurred before instead of after, the only things that really change are this number. It was 5 before, but now it's 4. And then this one changed because I'm changing what time it occurs at. Okay, so going from there to there. These behave very, very similarly. So using this idea, there's a way to rigorously describe how to combine these things together, and it's what's called the Kleinerman-Macedon board game argument. If you notice that you have this type of symmetry with respect to particle label and times, if I flip times, then you can set it up so that I can rearrange my sum before I do a triangle inequality. If I rearrange it correctly, I can show well-posedness, global well-posedness of this big infinite set of coupled equations. So in particular, what we ended up working with was I take polynomially weighted L infinity, and I define the one particle space like that. The K particle space, this just stands for the symmetric tensor product. So I just take, I take X1 and I just look at copies of it that are symmetric with respect to permuting variables. Okay. The natural space that this F lives in is going to be the product of all of these, where I'm defining, I'm lifting the norm on each of the spaces to the product by this L infinity weighted norm. So what I'm doing is I'm taking the supremum of whatever the norm was of my K particle system, and then weighting it with e to the mu K, where mu is what's called the chemical potential. And so joint work with Joachim and Patsoglu, my advisor Natasha, and Maya Taskovich, we can show using this Kleinerman-Macedon board game argument, abusing that, you know, that a lot of these diagrams look the same, you can rearrange the sum before doing a triangle inequality to show that this Boltzmann hierarchy has unique global solutions. So for all time into the space, if my weight is strong enough, so greater than 1, and Q is the velocity weight is big enough, where this gamma is corresponding to the law. So B of V minus V1 sigma is something like B of sigma times the V minus V1 to gamma. Okay. So we were able to show this by using this particle. Yes.
What if a single particle keeps hitting some other particles, or
so if I go to the infinite hierarchy, so it's only free flow. So what do you mean?
like say particle 1 hits particle 2 and then particle 3 and then particle 4?
Yeah, so if you do that, you have to take that into account in the analysis, right? But it ends up that you don't have too many of those terms. By rearranging them, you don't have too many.
So do you put a bound on it, like in terms of the probability?
So the way you end up doing it, so okay, the way this proof goes down is I can actually construct things very nicely by this Hewitt-Savage theorem. So I can construct solutions by looking at my equation and then formally using this representation theorem to construct a solution. The hard part's uniqueness. So what you do is you start with zero initial data because it's unique. Right? I mean, it's linear. The thing is linear. And then I start iterating. And so what I need to do is you end up writing things in terms of these expansions, right? And you just want to show that there's going to be some number that I can get if I keep going up in my expansion that's less than 1 raised to a big power, right? So if I can bound f of 1 in terms of some constant to the like 10,000 times whatever the norm of f to f 1,000 is, then I'm good. So that's how you close those kinds of estimates. If you can iteratively use this Dyson series to get smallness. Okay, cool. So this was the Boltzmann hierarchy. Another example of a collisional theory that's not particle-based is what's called the kinetic wave equations. So here, the fundamental object is a wave. So consider this equation. I have transport on the left-hand side of f, where f denotes the probability that a wave of a certain number, a wave of a certain amplitude occurs, right? So v is now like a wave number. Okay, and x is some localizing thing in positions. Okay, so what you get is, let's say I start from nonlinear Schrödinger. So this is work by Dung and Hani. And I start from nonlinear Schrödinger on a torus of size L. And I have some weight parameter. So just this is a interaction parameter. If I take L to infinity, this quantity to 0, and then look at the distribution of waves from this object. So I take the Fourier transform and look at distributions of the squares. What you'll end up recovering is an equation like this without the v dot grad x term. Okay. What it looks like is I have a product of 4 things, really 3 things, because if I multiply this out, right, I just pick up one of each, or I get all combinations. And what I'm doing is by integrating over Dirac of sigma, for example, means I'm integrating over the set of waves that conserve energy. So I'm looking at average effects of things that conserve energy, and they conserve, so this conserves energy, that one conserves momentum, right? Okay, and so one way we would like to understand this object is by looking at, okay, what happens. I can view this as being a very particular example of a more general theory. So you can form a hierarchy in a similar way. Okay, so if we do that, because the collision operator for this 4-way kinetic wave equation depends on 3 things. The resulting hierarchy that occurs is one that I index by 2 higher. So my f of k is dependent on f of k plus 2, because I'm adding 2 waves each time. And so again, it's transport, and then I'm averaging the contributions of what happens when I add in 2 new waves. And again, if I look at tensor products, it behaves nicely and agrees with the equation. So by considering hierarchies like this, we're considering generalizations of the 4-wave equation to non-chaotic initial data. So things that do not look like IID initial data. Okay. So using tools that were kind of developed for the Boltzmann equation, there's a nice paper by Toscani on how to use that. Because I'm inhomogeneous, I'm transporting, and I can use the weight to my advantage. If I have L infinity weighted spaces and positions, and I'm transporting, I can use that decay to get me better estimates to close some particles. So our first result with those authors is in polynomially weighted L infinity spaces, same as the ones we saw for Boltzmann. This kinetic 4-wave equation has unique global and time solutions for sufficiently small initial data, so small with respect to these L infinity waves. Additionally, you can also play a version of the Kleinerman-Macedon board game, which is combinatorially a little more complex, because every time in the previous one for Boltzmann, every time I add in a new particle, I'm looking for only symmetries when I flip one thing. But because I'm adding in two waves each time, I need to play a more complicated board game. I need to play a more complicated kind of analysis combinatorial game to figure out how to combine all of these sums together. But if you do this correctly, you end up with this theorem, which says that the kinetic four-wave hierarchy has unique global and time solutions. And again, there's this condition of either I have a very large mu from before, so a large enough chemical potential, or sufficiently small initial data. So long time, small data. Okay. Great.
What about large data but local existence?
Large data, local existence. I think, so we were aiming at long time results. So you can do short time stuff, and it does just look like a contraction. You can actually go to bigger spaces. Yeah, that's all I want to say. The reason we have to play this board game is actually because of the long time aspect of this problem. If I was not to recombine, if I was just to take short time, we could close a lot of estimates. But if I want a global in time thing, I need to be very careful. Okay. Any other questions? Cool. Okay. So we've talked about mixtures of a single species of particle, right? What happens when I take two species of particles? For example, I like this picture. I'm imagining a gas of like bowling balls and ping pong balls flying around in a vacuum. How do I effectively describe the statistics of this system for very large n, like red n and blue n? Like how would I even do that? So it turns out that the issue here, why this is hard to phrase, is there's an asymmetry in the way the blue particles behave and the red particles behave. So it's hard to find a theory that will encompass both. But it ends up you can do this. And so what you get at the end, if you work very hard, is this was written down in the literature after this is a generalization of the Boltzmann equation for mixtures. So here you can view F as being, for example, the probability distribution of the red particle, an average red particle, and G is being an average blue particle, right? And what it'll look like is, so the first line is, okay, regular Boltzmann, plus, and then there's some correction where there's a collision occurring between a red particle and a blue particle. Same for G, but the collision happens backwards. Okay, and so actually this was the first problem I was given in my PhD, was to like figure out how to derive this thing. So after many hours of like writing on big pieces of paper, you can write down this formula, which you can derive from the hard sphere dynamics. So I have a mixed hard sphere dynamics of bowling balls and ping pong balls. And I look at the Liouville equation, I do some fancy calculus, and you can narrow down what this expression is, where instead of having a subsystem of just a single index, I need two indices to describe the system. So this double superscript, K means the number of red particles, say, and L means the number of blue particles. So what it is it's just transport of these, the free transport of those particles, but there's a correction coming from, okay, I add in a particle of type alpha. So alpha could be either another red or another blue. And then when I collide, if I look at this picture, right? If I collide like a red particle here, it could hit either a red particle or a blue particle. So that's what this beta stands for. So there's a very complicated collision operator, but if you count it, if I have two particle types, there's going to be four, right? So those are exactly those four operators. Okay, and so in order to show that actually, if I start from hard spheres and I want to show some sort of convergence, I need to pass through some sort of formal object like this kind of hierarchy. So analyzing this object becomes, it's combinatorially more difficult because instead of having just trees, I have colored trees. Okay. Great. Okay. Wow, okay, I have lots of time. So the last thing I wanted to talk about was recent work we did on quantum mixtures. So if I have things that are of quantum nature, I have two different types of statistics. So the things that we observe are only the square of a function, right? So if I have a wave function of two particles, I know that this probability density of these two particles, let's say it's a square, is equal if they're identical. So if I flip the variables, I get x2, x1 squared. So what this says is either when I flip variables for the wave function, I get a plus or minus 1. x2, x1. So this corresponds to two different types of statistics that you do not see on the classical level. So the first one is bosons, where I have symmetric wave functions. Now, if I have symmetric wave functions, it's very nice because I can actually form like an ansatz, a very nice trial state for these. So if I'm bosonic, that means I have a symmetric wave function. If I define this big wave function of the n particles as just being the tensor product of a simple one, again, all this notation means is I'm producting from I equals 1 to n of phi of xi. If I look at this object, right, it's immediately permutation invariant, right? The other type of particle, so if I do this, by the way, this is what's called a Bose-Einstein condensate. This is a Bose-Einstein condensate. So what it means is if I take a state, for example, like an n particle state, and I start cooling it down, right? There's going to be a minimum energy level that this big wave function of n particles has. If I cool them down all to the same state, actually all of these will be the same and they'll just be the ground state energy. So I can start filling up this is my energy levels. Okay, and so you can actually macroscopically observe this. This is Katerla and another group in 1995 got the Nobel Prize by super cool things and use this idea. I can macroscopically observe my wave function. Okay. For fermions, though, I don't have this picture, right? If I look at this and I start flipping variables, I don't get a minus sign popping out. So you need a more complicated ansatz. So the ansatz that ends up being taken in physics a lot is if this is fermionic. So I take an x1 to an xn. What I would like is actually a determinant. So this is a phi I of xj. The determinant over this matrix of I and j, where phi I is orthonormal in L2, for example, like torus. So if I look at just this expression, I have a phi I of xj, and I flip a j. I get a minus sign popping out. That corresponds to flipping a rho. Okay. But what it means is because I have a full orthonormal set, I can't effectively describe this thing in a normal way, right? If I'm to try to take n to infinity, it's not like I have a clear object to pick out. That's like my macroscopic, my effective theory. Okay, also you can see this at the level of energies. So if I have a fermionic wave function, right? The anti-symmetry causes what's called the Pauli exclusion principle. So what it means is, even though on this picture on the right, I can supercool bosons, right? I can put them all in the same energy level, all cool them. For fermions, I can try to do that, but at some point there's going to be a degenerate, they call it the Fermi pressure, which says I can't put everything in the same state. Okay. And even though I can try and cool this thing, it really won't get that much smaller with the same time scale. Okay. So the question I want you to think about is, if I have two of these gases together, what does an effective theory mean if I mix two of them together? Let's say I exclude self-interactions. I exclude boson-boson interactions and fermion-fermion interactions. And I just look at a gas of bosons and a gas of fermions that are put together in some sort of optical trap and supercooled. Okay. What you end up getting is the following equation. So we were able to write down a derivation of an equation for this mixture. So this is with Esteban Cardenas and Natasha Pavlich. You end up having to use a more sophisticated language in order to take out a leading order theory. The reason for this is there are two different energy scales happening in the problem. So bosons have a much lower energy scale than the fermions. And in order to find a limiting theory, you need to figure out all of the parameters. You need to keep them kind of general in order to balance all of them at the end of the day. So our effective theory for a mixture of bosons and fermions, for example, is here omega is a trace class fermionic density matrix given by, so this is the bracket of the kinetic energy of the fermion weighted by its mass, plus, and then lambda is the interaction energy, the strength between boson-fermion interactions. And rho b is the position density of the bosons. For psi is the bosonic object, and it's just a regular wave function. And it's going to be the kinetic energy plus lambda times m times the interaction energy. So here there's going to be a rho f and a rho b. Each of these equations are coupled this way. So v is whatever the interaction is. Okay, and so what we show is if I take this effective theory, so this is just a PDE, and I look at n bosons and m fermions evolving in a box, what I can get is that the solution of my PDE is close to what I call the one particle marginal of my fermionic system. So if I was to take a one particle marginal of this object, this actually ends up being what's called the, you can just look at it like this. This is phi. Anyway. In terms of Browsing-Ketz, if you know that language. Okay, and similarly, so this is the fermionic thing, is less than or equal to, okay, I have a 1 over m, which is the number of fermions, times some exponent, right? And there's a bunch of parameters. Similarly, for the bosons, if I look at the leading order, I pull off the leading order piece. So this just means projection onto the wave function generated by this phi, where phi solves this equation. Then I get another bound where I have a 1 over square root n popping out. Okay, and so the only thing in order to get some sort of limiting effective theory to say that this equation describes the dynamics of the marginals associated to these, I just had to check that this constant doesn't get too big. Okay, so that's part of our theorem. The other is if I look at very particular scaling range. So for the fermionic piece, I know classically in the literature that if I take the Wigner transform of this, so I take a semiclassical transform, take h bar to 0, so h bar is Planck's constant, then I can obtain the Vlasov equation as the limiting difference. Okay. If you do this for our situation, so if I take Planck's constant to 0, in addition to taking a mean field, and we needed to take very, very light bosons that were very numerous in order to balance all those constants you saw before. You can actually derive something we call the Vlasov-Hartree equation, which is I have F is my fermionic density. When I take the semiclassical limit, it just behaves like a classical probability distribution. And for the boson part, it's going to be a dispersive equation. It looks like Hartree. So here I'm excluding, there's going to be, if I included boson-boson interactions, there would be an extra nonlinear term here for phi. And if I was to include fermion-fermion interactions, there would be an extra nonlinear term associated to this part, same as in Vlasov. Okay, and we actually could show quantitative convergence. If I start from this Hartree system of equations, I can show that this effectively describes, solutions of this effectively describe my gas with quantitative rates. And we were able to do that using quantum optimal transportation. So whatever the analog of optimal transportation is, which is very useful for Vlasov, you can use it here, where I just, instead of tracing out, if I have I can formulate things in terms of matrices, basically, and operators. Okay. I think that's all I wanted to talk about. If you have any questions, please.
Questions or comments?
So for the collision, do you consider if there are like more than two particles, they line like at center?
If there are more than two particles,
Yeah.
you ask, oh, in what context? More than two species of particles, like types of particles, or?
The two pictures you said they are kind of similar.
Yeah.
Like under this situation, because you only in the picture you only have two particles, right?
Yeah.
Big line. But what happens if you have like maybe 3 or 4?
Yeah, so you
Line
can
like
do that.
center.
There is versions you can do for higher order particle collisions. So so for the wave turbulence stuff, you often get trees that look like that. This is why they call it the four-wave equation. Is if I drew that same tree, this is like the four-wave equation. But also so this is waves. But for particles, if I have n particles in a box of diameter epsilon, right, I can actually consider what happens when I just make up a scenario where I collide 3 of them at the same time, right, and they all bounce off. And I do it in such a way that it preserves conservation of energy and momentum. So this actually results in a variant of the Boltzmann equation. So this is going to be this, where instead of taking, if I have n particles, I need epsilon to the d minus a half. So this is like a different scaling than so this is the regular Boltzmann-Grad scaling. This is Boltzmann-Grad. Okay, I don't know if that makes any sense, but you can do higher order versions of the particle story, and that makes sense. So this is due to Epatoglu. And I think there's a paper by Warner also, and Pavlovich. Okay. I don't know if that was your question, but.
Yeah, so like what happens if you have the mixture, say like Q?
Oh, for mixtures, that's not something I've thought about. For higher order,
Okay.
Not sure. I think you could do it. It would just, so the hierarchy version of this. So for mixtures, every time I add a new mixture, I add a new direction to my hierarchy. It's like a vector hierarchy. If I add in more higher order collisions, what I'll get is the operator will depend on higher and higher marginals, right? So it'll be transport of Fk equals collision of, here it'll be k plus 2. If I added in another F, it'd be k plus 3.
Questions?
Yeah.
Do people care about having solid boundaries in terms of kinetic equations?
Solid boundaries. So there are.
So when you say we're thinking about n particles interacting or not, do we see them as in Rn or?
So there is one result I know of where you can derive, for example, Boltzmann on like the half space. So that is, I don't think if I have a closed box, right? I think it's quite difficult actually, because one of the hard things about deriving a Boltzmann equation is in the finite particle flow, I have collisions, right? And this infinite object, the Boltzmann hierarchy, it just has free transport as this generator. So if I want to compare those two things, I somehow have to exclude the fact where I recollide with something. Okay, and so if I end up in the situation where all my particles are bounded in a box, I believe my intuition feels like you should be using some ergodic theory to say, okay, there's actually many free collisions that will happen. So I'm not sure you can actually do it. Yeah.
Are there any experiments
Yes, so
that actually show this fermion boson
yeah.
interactions?
Yes, so this is where this started actually. So this is a paper. Oh, I should write it again. These are not my pictures. So there is a lab in Chicago. So this was the pictures I got are from a survey article back in 2002. But there's a lab in Chicago that are creating degenerate gases of bosons and fermions. And the reason they care about these things is when I start mixing these two quantum effects and supercooling them, you can end up tuning interactions between bosons and fermions. So it ends up being like a physically very relevant theory to consider. The issue though is even in a lab, when I try and cool these things, the energy levels are much different. So let's say I make a Bose-Einstein condensate and try to put a Fermi C inside of it. I can only have a certain number of particles of fermions. Otherwise, whatever containing force this boson cloud has is not enough to contain the energy of the Fermi C.
So what happens?
You end up losing fermions, or it destroys the
Losing
condensate
fermions.
in the optical trap. So
Oh,
I have it's usually an optical trap from what I see. So it is a fairly physically relevant system. Maybe not in that scaling regime.
Yes. Any other comments or questions? Then let's thank Joe again.